Okay, so again, making sure we look at the recurrence formula as well as the bit that says prove that. So first thing we want to do is check out, in this case it's going to be U1, and you can see, you can even say U1 in the recurrence formula here. We're given U1 is 7, so we're just checking this out to see if it all matches, so hopefully we get 7. So we've got 13 times 7 to the 1 minus 1, which we know is 0, plus 1 on 2. So we've got 13 times 7 to the 0, so times 1, plus 1 divided by 2, which is 14 on 2, which is 7. So we're all good. So it matches our recurrence formula. Alright, so U1 looks good. So we're saying if our P of k is true for some arbitrary integer k is greater or equal to 1, then we have got UK is 13 times 7k minus 1 plus 1 all on 2. Alright, and what are we required to prove? We're required to prove our P of k plus 1. What is that? So we've got our U of k plus 1. We want it to equal 13 times 7. Now we've got k plus 1 minus 1, so that'll be k plus a big 1 there on 2. Alright, so let's look at our left-hand side of that. So we've got U of k plus 1, and we can say, using our recursive or our recurrence formula, U of k plus 1 is going to be equal to 7 UK minus 3, using recurrence formula. Alright, and then we can use that. So using our P of k here, here's our P of k. We've got 7 lots of all this stuff. 13, 7 to the k minus 1, plus 1 over 2, and then minus 3. Alright, remember we're trying to get it to look like that. So it's all one fraction, and it's got 13 times 7 to the k. So you can see here what we're going to do is we're going to put that 7 through, times that through. So 13 times 7 to the power of k minus 1 times 7 will be 7 to the k. And then 7 times 1 is 7, right, all over 2, minus, now it's nice and easy, I've taught you this before, I want a common denominator of 2, so that's going to be a 6 on 2 for that minus 3. Alright, so what does that give us? We've got the 13, which is what we want up here. We've got the 7 to the k, great. We've got plus 7 but minus 6, which is plus 1, great. That's what we wanted on 2. Alright, so that gives us our right hand side. Therefore P of k implies P of k plus 1. Therefore P of n is true for integer n is greater or equal to 1, and we've done it by induction.